Hey everyone, my name is Bryce. I'm a former student at Queen's University, and what I'll be doing is I'll be leading you guys through a series of reality checks, which are videos that we've introduced to the course to provide some context and some real-life applications for some of the material that we're learning throughout the course. So for this first reality check, we're going to be talking about lubricants and their various applications, how they can be used to reduce friction between various moving mechanical components, which in turn can reduce wear and improve the life of various machines. So when we're talking about machine lubricants and where they can be applied, they can be used for transmission systems, engines, gearboxes, and pretty much any mechanical system that requires contact between moving components. The most important property for a lubricant is in fact its viscosity, as we've discussed in class. So when you're selecting the viscosity or selecting the lubricant for a given application, what you need to concern yourself with is what viscosity is required to actually maintain a boundary film layer to prevent contact between mechanical components during its application. So the higher the viscosity of the fluid, the better it will protect moving components from one another and prevent wear within the system. But on the flip side of the coin, you need to consider the fact that higher viscosity means higher viscous friction forces and more heat production due to those viscous friction forces. As an additional concern, if the fluid is too viscous, it might be very hard to distribute it throughout the machine. An additional concern to keep in mind is how the lubricant's viscosity will vary with temperature. Now, all fluids have a temperature-dependent viscosity in that as temperature increases, viscosity will decrease. But what you need to keep in mind is what the range of operating temperatures for the machine would be and what your steady state operating temperature will be, and that's what your target viscosity should be made up for. So for actual industry applications of a lot of lubricants and oils, namely gearbox oil or engine oils, what you find in reality in industry is that they're actually rated not by their measured kinematic or dynamic viscosity, but instead rather by a rating system which is classified by a rating agency such as AGMA or SAE. We're going to actually look at a couple examples of SAE rated motor oils, and I'm going to quickly run through how their classification is made up. So for an example of industry rating classifications for an actual application of lubricants, we're going to talk about the SAE grades of motor oils. So I've got a couple here. This is what we would call a unigrade oil, and we've got a multigrade oil here, and we'll kind of run through the properties of a few of them. The SAE rating system is rated on a scale from 0 to 60, which correlates roughly to viscosity at operating temperatures, but also the SAE rating, they've got a standardized curve which corresponds to viscosity as a function of temperature. And I'll show that in a chart in just a minute. But for the unigrade oil, we have an SAE 40 oil here. So that's a relatively heavy oil, relatively high viscosity. Now, multigrades are a little bit more complex. These ones have been designed such that they don't follow one strict SAE curve, but rather, as the temperature changes, they'll switch from one standard curve through to another. This might be a little hard to explain, but we'll show on the chart in a minute. But essentially at low temperatures, minus 40 through to plus 10, and then transferring up over to the 100-degree operating temperature, at low temperatures it'll behave like a 0 rated oil. And then as we reach the operating temperature of around 100 degrees, well, it'll behave a lot more like a 20 grade oil. Okay, so when we look at the chart here, I'll make a comparison between, so we have water here at the bottom, and then SAE 30 oil, and then a multi-grade 0W30 SAE oil. And what you can see when you compare the two oils together, so at low temperatures, 0 degrees, on this logarithmic scale, it's not a very clear difference, but the SAE 30 oil is actually about 2 times as viscous as the 0W30 oil, which means that when you're starting from a cold start, it's going to be very viscous, very hard for it to be distributed amongst various mechanical components. But then as the temperature increases, the curves get closer together, and at this point, the difference between the two curves at about 100 degrees Celsius, which is the operating temperatures, is going to be much, much smaller. So that's where the 0W30 comes in. So it'll start behaving similar to a 0, and then as the temperature increases, it'll approach the point of the 30 oil curve. You'll see that both of these actually are very much more viscous than water. So if you can imagine the viscosity of water. So we look at the order of magnitudes of water's viscosity, and we'll see that we're always looking at between 1 and 2 orders of magnitude more viscous. So, you know, in the range of about here, we're looking at something similar to the viscosity of honey at room temperature. So now we're going to use a couple of examples of pouring SAE oils down a plate to show you exactly what I'm talking about when I'm talking about the difference between a light and a heavy oil or a cold and a hot oil. So just as a comparison of the relative viscosities of a couple of oils we have here, we've got an SAE grade 40 oil and then a SAE 0W20 grade oil. And obviously the 0W20 is going to be a much lighter oil. It should be a fair bit less viscous. So it's going to, in this example we're going to do here, we're going to pour both these oils down this plate. We're going to see that the lighter oil, the castrol edge, is going to flow a lot slower.
I think you meant faster, Bryce.
For this test, we're using the same oil, the SAE 40 oil, for both the left and the right side. What we have is the oil on the left here has actually been cooled down in the freezer to about 0 degrees Celsius, whereas the oil on the right is about room temperature. Okay, a bit more than room temperature. It's a very hot day, but as you can see, there's a big difference in the temperatures between the two of them. And when we start to pour them down the plate, you'll see that the cold oil pours a lot more like thick honey, very viscous, and it takes much longer to flow down the plate than the room temperature oil. This shows the temperature dependency. So now, after seeing a little bit and learning a little bit about viscosities and their applications in lubricants, you can appreciate a little bit about why we're learning about viscosity in a fluid mechanics course and what its value is when you actually go out and work as an engineer.